All right, hey everyone, let's talk about linear differential equations today. So we've talked about separable differential equations, we've talked about general differential equations, and we have talked about how that can be applied to electricity and magnetism, exponential growth, kinematics, forces, all some great stuff that we can look at differential equations for. Today we're going to look at some more complicated equations called linear equations. If you take BC Calc, you are off the hook for this one, but if you are in Calc 2, you are not off the hook for this one, so stay back and check this out. So linear differential equations can be best described as being equations that take the form of our derivative is equal to p of x, some function of x, times y equals q of x, which is some function of x. So both p of x, and q of x are going to be continuous, and they are also going to be differentiable. Which are always two good kind of preconditions that you have when you're dealing with any sort of calculus. You want to make sure that it's differentiable. You also want to make sure that it's a continuous function. So this just means it is not like a silly function. It behaves well when we're dealing with calculus. But anyways, that's besides the point. You can see kind of a linear relation, right? We've got some something times y plus something times 1, right? So we've got some sort of linear relation there. So we're going to exploit that. And the way that we deal with this is what we are going to do is we're going to define some integration factor. So what you're actually going to see is that you can look at this kind of in terms of a product rule, and that's going to come into play really well. So what we do is we apply an integration factor to everything. So we define our integration factor as the exponential, the integral of p of x. So this little guy here, we define that in our integration factor. So we take the exponential of the integral of p of x, and we multiply everything by this integration factor. So when we multiply everything by the integration factor, what we are going to find is that this side of the equation is going to look a lot like the derivative of something using the product rule. So then we can write, it's usually going to be, so this is going to be the derivative of a product of two functions, let's say x times y, and then that's going to be equal to some q of x times I, or something like that. Then you're going to integrate both sides. Then that's going to be fine. You're just going to get xy. Then that's going to be some other expression. Then you just start going to divide by x so that you isolate y. Then you've got your solution. All right, let's do an example, right? So let's find the solution to the differential equation dy dx plus 6x squared y is equal to 12x squared. Okay, so first what we want to do is we want to identify what our terms are. We've got our q of x here, and we've got our p of x here. So what we are going to want to do is we are going to want to define our integration constant, or our integration factor. So our integration factor, if you remember, is equal to the exponential of the integral of p of x dx. So we're going to take the integral of 6x squared, and then we're going to take the exponential of it. So I is equal to the exponential of the integral of 6x squared dx. So if we integrate that, and then we're just going to go back to the e to the convention as opposed to the exp. So we get e to the 2x cubed. Okay, so now we're going to multiply everything by e to the 2x cubed. So we get e to the 2x cubed times dy by dx plus 6x squared e to the 2x cubed y is equal to 12x e to the 2x cubed. Okay, 12x squared e to the 2x cubed. So what we are going to find is that this looks like a product rule expression. We have y here. We have the derivative of y here. We have x here. We have the derivative of x here. So as you can see, we've got kind of a product rule situation. And so we're going to take the terms that aren't differentiated. So this is really going to be equal to the derivative of e to the 2x cubed times y, right? So that makes this all easier for us. So we get the derivative of e to the 2x cubed y is equal to 12x squared times e to the 2x cubed. So what we're going to do is we're going to integrate this expression, we're going to integrate this expression. We can integrate this expression easily because the derivative and the integral cancel out. However, on this side, we've got to do maybe a mental u substitution, right? Because we've got order 3 up here, we've got order 2 there, so we're going to have some nice constant, right? So e to the 2x cubed y is equal to integral 12x squared e to the 2x cubed dx. All right, so we integrate that. We get e to the 2x cubed y is equal to, sorry, this y there should not be superscripted. It should be down there, is equal to 2x, or 2e to the 2x cubed. So we're going to divide everything by e to the 2x cubed, so we isolate y. And then we also add our integration constant. Don't forget that. We haven't imposed an initial value. So we get y is equal to 2 plus c over e to the 2x cubed. So that is how we solve a linear differential equation. So this can be applied actually quite a lot to the field of circuitry. So we'll do an example with circuitry. So let's find a function of I is a function of t, such that R is equal to 12 ohms, L is equal to 4 henries, and E is equal to 60 volts. And we're going to have an initial value such that I of 0 is equal to 0. Okay, I threw out all of these constants for you. You probably have no idea what they mean if you haven't taken whatever it is, AP Physics C or something. So here's the equation that we use. We use L di dt plus R times I is equal to E of t. Now this is obviously a linear differential equation. But as you can see here, we've got this pesky L factor here, so we're going to need to divide that out at some point. So plugging in our values, we get 4 di dt plus 12i is equal to 60. Well, that's great. We can divide everything by 4, and that leaves our di dt as monic. So we get di dt plus 3i equals 15. Now we're going to have a really nice easy integration constant. As you can see, it's just going to be 3. So we get I of t is equal to the exponential of the integral of 3 dt. That's one of the easiest integrals we could possibly do. We get e to the 3t as our integration factor. So we're going to multiply everything by e to the 3t. We get e to the 3t di dt plus 3i e to the 3t is equal to 15 e to the 3t. Okay, we can recognize we're getting used to recognizing the product rules. So we get d by dt of e to the 3t times I is equal to 15 e to the 3t. So thus we get, we need to integrate both sides. We get e to the 3t I is equal to integral of 15 e to the 3t dt. Again, maybe a simple u substitution, or maybe even no u substitution, hopefully. At this point, you guys should be rock stars at this substitution, change of variables rule, whatever you want. So thus we get e to the 3t times I is equal to 5 times e to the 3t plus c. Okay, so now we solve for I. So we get I of t is equal to 5 plus c e to the negative 3t. All right, so now we're going to impose the initial value problem such that I of 0 equals 0. Thus we get I of t is equal to 5 minus 5 times e to the 3t dt. Or no dt, just e to the negative 3t. Right, we're dividing, we get the negative exponent. It's too used to saying dt's at this point. All right, in the next video, we are going to talk about differential systems, ecological systems. Then we're going to be moving on to sequences and series, which is usually considered one of the hardest units of not only single variable calculus, but also multivariable calculus. All right, we'll get to that in the next one. See you guys later.